Hey everyone, welcome back to the Advanced Math Series. I'm Mr. Hunt, and today we're diving into Lesson 7, where we'll be tackling 7a, Inductive and Deductive Reasoning, 7b, Logic, 7c, the Contrapositive, and 7d, Converse and Inverse. Now, as you guys know, I'm going to be out this week, and I wanted to come up with some videos for the next couple of lessons so you guys aren't left out. I've been playing with all these new digital toys, and Joe's been helping me out a lot. Thanks, Joe. The last video was done on Microsoft Whiteboard, and the next two lessons are going to be done on OneNote. I want you guys to tell me which ones you like better, what's more appealing. As always, feel free to pause and rewind whenever you need to. Don't forget to request help through the group chat or on the stream. Now grab a notebook, get comfortable, and let's get started. Right into 7a. We're going to be covering inductive reasoning. I know you have your bookwork. I asked you to read your bookwork. It's kind of lengthy, a lot of words, not a lot of math, but it'll come in later. So I've just put some extra curricular writing so you can see some more examples, and we'll get into some more problems later. I'll just read this to you real quick. Inductive reasoning involves generalizing based on specific observations or examples. It's like noticing a pattern and then assuming that the pattern will continue. Some examples. Let's see. Imagine you observe the following sequence of numbers: 2, 4, 6, 8. You might notice that each number is 2 more than the previous one, and using inductive reasoning you might induce that the next number in the sequence will be 10. Deductive reasoning. This involves starting with a general principle or rule and applies it to a specific case to reach a conclusion. It's like using a known fact to prove something specific. Examples. Alright, consider the general principle that the sum of the angles in any triangle is 180 degrees. If you have a triangle where two angles are 50 degrees and 60 degrees, you can use deductive reasoning to conclude that the third angle must be 70 degrees, since 180 minus 50 minus 60 equals 70. So in summary, for 7a, we have inductive reasoning. Basically, you have specific observations will lead to general conclusions, and deductive reasoning, general principle, will lead to a specific conclusion. And that's basics right there for 7a. Alright, lesson 7b, logic. Logic, there are a lot of terms involved here, and we'll go over them briefly. You can read these on your own as well. We'll talk about syllogisms. Syllogisms is going to be a form of reasoning where a conclusion is drawn from two given or assumed propositions. We call those premises. Each of these premises share a common term with the conclusion. Categorical propositions are statements that relate to categories or classes. They're going to come in 4 types. I know, I think the book only mentions 2. If not, who cares? Let's go over this. We got universal affirmative. That's where we're going to be of all S are P, right? So the example would be all dogs are mammals. Where you have your universal negative, no S are P. So no dogs are reptiles. Particular affirmative, we have some S are P. Some dogs are friendly. And a particular negative, some S are not P. So some dogs are not friendly. Let's go more over to the universal affirmatives here. A universal affirmative proposition states that all members of one category are included in another category. For example, all humans are mortal. We have major and minor premises in a syllogism, right? The major premise is the more general statement that includes the major term, the predicate of the conclusion. For example, all mammals are animals. The minor premise is the more specific statement that includes the minor term, the subject of the conclusion, basically. For example, all elephants are mammals. Examples of syllogisms. Let's put it all together with some examples here. We have the major premise here. All mammals are animals. It's a universal affirmative. A minor premise. All elephants are mammals. A universal affirmative. Conclusion. Therefore, all elephants are animals. In this example, the major term is animals, the minor term is elephants, and the middle term, which I don't think is covered in your book, but we can probably deduce if it wasn't. The middle term is going to be mammals, which links the major and minor premises. How do you even say that? All right, summary. Syllogism. It's a logical argument with two premises leading to a conclusion. Categorical propositions are statements that relate two categories. Example would be universal affirmatives. Universal affirmatives. A type of categorical proposition stating all members of one category are in another. And you have the major premise, which is the general statement in a syllogism, and minor premise is the specific statement in a syllogism. All right, as I like to do, I like to color code things. Maybe explain this a little bit better. I did mess with this OneNote here a little bit, so if I can bring in my tools, go to a little laser pointer. All right, maybe you can see this, maybe not, I'm not sure. But we have all men. I put these little set brackets in here to show you. It's all in red. This is going to be every member of a set, right? All men are mortal. This is the major premise. Aristotle is a man. This is the minor premise. Therefore, Aristotle is mortal. Conclusion. This conclusion is logical. Now let's see why. So in your major premise, we're going to be establishing mortality as possessed by every member of a set. So all. That's a big word right there. All. Universal, right? All right, and your minor premise is going to be, it's going to identify Aristotle as a member of a set of men, right? The conclusion is that Aristotle, which has been identified as a member of this set, is mortal. I always like to look at it like this, and I don't think the book covers it well. A equals B, right? You can see that all men equal mortal. Then you have C, Aristotle. He equals the group of all men. Therefore, Aristotle is mortal, right? All right, this is going to make your conclusion logical. I hope that color coding and this A equals B, C equals A, therefore C equals B helps. I know it helped me. All right. Now let's look at this little statement that's, I think, in your book here. The sum of the exterior angles of a convex polygon is 360 degrees. Triangle ABC is a convex polygon. Therefore, the sum of the exterior angles of triangle ABC is 360 degrees. But wait a minute, hold on. Don't triangles have 180 degrees? Yes. This is a three-step process. It's called an argument. That's what you're going to be dealing with a lot in this lesson here is arguments. In syllogistic reason, focus goes to the argument and not the truth or falsity. Okay? So, this is actually what would be called a valid argument. Right? Even though we know this is false, we're not looking for truth or false in an argument when we're asking, is it a valid argument? We're asking if our A equals B, right? Did our major premise here, what was it? Let's go back up. Did it establish, right, something? It did. Our set is going to be the sum of exterior angles of a convex polygon. That's the set, right? And that's going to be equal to 360 degrees. Then we bring in our third variable, C, triangle ABC, and they identified, the minor premise, identified this as a member of the set of convex polygons. Therefore, the exterior angles of this triangle is 360. As you can see, we still have our C equaling B because it was identified as a member of A. So this is a good argument, but it's totally false. Let's look at some more. All frogs are green. Henry is a frog. Therefore, Henry is green. All right, we have our universal here. All frogs, set. All frogs. They're going to equal green. All frogs are green. Awesome. Now Henry, he's a frog. He's been now identified in the minor premise, identified as a member of the set of all frogs. Therefore, Henry is in fact green. That's a valid argument. Okay. Now, let's go over this one right here. If it rains, I will go to town. If it did not rain, therefore, well, no, not if. If it rains, I will go to town. It did not rain. Therefore, I did not go to town. Now we're introducing some ifs. We're talking some conditional stuff. All right, this is not an all. This is not a set of everything all. So this is going to be failing to establish a set, such as if it rains this weekend, right? Let's say if it said, if it rains this weekend, I will go to town. All right. It did not rain this weekend. Well, therefore I went to town, because now we're actually identifying a set. We didn't ever specify which day, and it's a big if. So like I said, this minor premise also doesn't identify a member of a set that's defined by the major, right? So it did not rain, just a statement here. So this is faulty, and it would be called an invalid conclusion. All right. All right, let's go ahead and start on example 7.1. The book's going to ask you, is the following argument a valid argument? Why or why not? And the argument's going to be in 3 parts. All normal dogs have 4 legs. That dog has 4 legs. Therefore, that dog is a normal dog. Well, we can look at our set. Is it universal? Yes. All normal dogs, right? Equals 4 legs, right? When we have that dog has 4 legs. We have A is equal to B. We have our C is equal to B. And then therefore that dog is a normal dog. All right, so this argument is going to be invalid because the set described is all normal dogs. The minor premise should have stated a particular dog was a member of that set, but it did not. So hope you understand that one right here. Let's go to example 7.2. Same thing. Is the following argument valid? Why or why not? All boys are good. That child is a good child. Therefore, that child is a boy. Invalid argument. I mean, you can already see it right here. We have a set of all boys, and then the person here is a child, right? That child. The premise is failing to identify a member of the set, right? It's like, okay, the minor premise is that this child has to identify this child as a boy, right? Be all boys, but it doesn't say that. So it's failing to identify the member of a set. It'll make it invalid every time. Look out for those keywords. Example 7.3, we'll go with, is the following argument valid, yes or no? All right. All chickens have 3 legs. Henny Penny is a chicken, therefore Henny Penny has 3 legs. Sounds pretty legit, right? So all chickens, right? Chickens equal 3 legs. Henny Penny equals chicken. All right, well, as you can see, we have our A equals B. C equals A, therefore C equals B. It's going to be a valid argument. And remember, we're not going to care about the truth or falsity when assessing if the argument is valid or not. We know that chickens typically have 2 legs. If they had 3, I guess B-dubs will be in business and they could probably sell chicken legs cheaper. Supply and demand, right? Okay, now back. We'll be on lesson 7C in the contrapositive. All right. This is one I like. We have if-then statements. An if-then statement is also called a conditional statement. It has 2 parts. You have a hypothesis, which is the if part, and the conclusion, the then part. So if this, then that, right? This is going to be used all over the place. A lot of coding. So I just showed you real quick for Microsoft Excel, which I use a lot. You can code in some if statements. So if, you'll have your open parenthesis bar, you'll have your logical test, separated by a comma. They're going to want the value if true and the value if false. Close parenthesis. Bam. Now you can test cell A2 against greater than A3. If that's true, I want a yes. And if that's false, I want a no. And bam. You're in Excel. But we're not doing Excel. I'm just saying if-then statements will be in all kinds of computing. Your hypothesis, I'm going to be trying to best I can color code is red, conclusions blue. All right, you got if-then statements. All right, so we have an example here. If it rains, then the ground will be wet. So that's a hypothesis, and then the ground will be wet is the conclusion. That's pretty logical, right? All right, negation. Let's talk about negation. Negation sounds a lot like negative. That's exactly what we're doing here. Negation involves making a statement the opposite of what it is. If the statement is P, then its negation is not P, written as tilde with a P, right? Not P. Said is not P. Let's talk about the contrapositive. You can see I did purple for contrapositive. The contrapositive of an if-then statement is formed by negating both hypothesis and the conclusion, switching their places basically. So you would have P, if P, then Q, or we'll reverse that. And you'll have if not Q, then not P. So it's basically your premise in reverse, your if-then in reverse, and both negated with a not symbol. All right, for the statement if P then Q, P then Q, the contrapositive is if not Q then not P. Just covered that. Example, if it rains, then the ground will be wet. So the hypothesis is if it rains, the ground will be wet. Therefore, if we said no, it does not rain, then the ground will not be wet. You see how that makes sense? That works. The contrapositive, if the ground is not wet, then it does not rain, or it did not rain, rather. All right, summary. If-then statements. All right, if P, then Q, right? If it rains, then the ground will be wet. Negation. Not P, not Q. It does not rain, the ground will not be wet. I think that should have been an arrow. Contrapositive will be the reverse and negated. So if not Q, then not P. If the ground is not wet, then it did not rain. All right, the contrapositive of a true statement is always true. If it rains, then the ground will be wet is true. Then, if the ground is not wet and didn't rain is also true. It's a good thing to remember. Let's go over to, actually I left this big blank area because it's going to represent the Venn diagram the book had for fast rabbits, I guess. But we'll just do that with, I guess the ground, huh? Let's do it with the ground. It's not hard. Bring up my tools here. I want to have a big old box. This is the parking lot. Yay! All right. So in the parking lot, we're going to have our not Q, right? Not Q. This is going to be ground not wet. All right, let's put this over here. Ground not wet. And this Venn diagram is pretty easy. So we'll draw a big fat oval here. And we're going to have this another. Okay. All right. All right. So if it rains, right? Our rain is going to be our P. And then outside of our rain, well, let's go with yellow, shall we? Our Q will be out here. And this is going to be ground is wet. Right? And this is, does it rain? It rains. Okay. So if it rains, the ground will be wet. All right. If it does not rain, it will not be wet. And you can see your little arrows here, I guess, if you want. If P, then Q, we'll just reverse the arrow. Right? And then if the ground is wet, then it rained. Same thing, right? And then if the ground is not wet, right, not Q, well then, we're at not P, right? It didn't rain here, right? You can see there's no rain blue out here, so it didn't rain. That's what they're trying to explain there. That Venn diagram for the one in the book with fast rabbits or whatever. But we did the same thing with rain and wet ground. Moving on to example 7.4. Let me get rid of that. Is the following argument valid? All right, all non-athletes are vegetarians. Jim is a non-vegetarian. Therefore, Jim is an athlete. So we got a major premise here is a not P, right? Not can be used as not, non, doesn't. Either way, we have a set of all not P's. And they're going to be vegetarians. Okay, that's going to be our Q, our conclusion here. Now we introduce the minor premise, and we have to remember I have to identify them, right? So Jim is a non-vegetarian, so he's going to be equal to a not Q. And they're saying that Jim is going to be an athlete. All right, so remember, the premise can always be replaced with its contrapositive. All right, so let's do that. If non-vegetarian, then athlete. Okay, so on this one right here, we're not going to mess with the colors here too much, but a non-vegetarian, vegetarian is going to be Q, right? And he is a not Q. If not Q, then he is a P, right? He's an athlete. This down here is a non-vegetarian, so he's identifying Jim as a member of the set of all non-vegetarians. This is the minor premise. Remember, we only flipped the major premise because we turned it into a contrapositive. When we just turn it into a contrapositive, they're going to be equal. That's good to remember. All right. It's going to be a valid argument. So the original statement's also going to be valid. So the conclusion is not necessarily true, but the argument is valid. And that's it for this lesson. All right, moving along to lesson 7D, converse and inverse. All right, a lot to be said here. Let's see. Converse is the converse of a conditional statement is formed by switching the hypothesis and the conclusion. Pretty easy. If P, then Q, and we're going to switch it. No, if Q, then P, right? I don't know why the book doesn't tell you, but you could also, I don't know if you can also do this, but think of it like that. The converse, just going backwards. P, if P, then Q, or if Q, then P. For the original statement, if P, then Q, then the converse is going to be if Q, then P. Here's an example here. If it rains, then the ground is wet. If the ground is wet, then it rained. That's converse. Now we'll go to inverse. Inverse of a conditional statement is formed by negating both the hypothesis and the conclusion. For the original statement, if P, then Q, the inverse is going to be, well, if not P, then not Q. inverse. All right, for example, if it rains, then the ground is wet. The inverse is going to be, if it didn't rain, then the ground is not wet. Pretty simple. Just negating everything. We're going to have if and only if statements, also called biconditionals. The if and only if statements is abbreviated with the IFF, so if. All right. And it's true when both the original statement and its converse are true. It is written as P if Q. This means if P then Q and if Q then P. Okay, so this is biconditional. Think of a two-way instead of a one-way street. Now we're going to have both ways, and that's actually the symbol. I think we go over that later. So a number is even if it is divisible by 2. This means if a number is even, then it is divisible by 2, and if a number is divisible by 2, then it's even. Pretty simple. Conditionals are summary. The original will be if P then Q. The converse is if Q then P. The inverse is if not P then not Q, and the contrapositive is if not Q then not P. If and only ifs are, P, if and only if Q. So let's go over some color-coded notes that I wrote down here for whatever reason. All right, we have your premise. Your original premise is P equals Q. The contrapositive, I should have actually done this one next. All right, the converse of the premise is going to be the premise backwards, right? Q, if Q, then P. The inverse is going to be if not P, then not Q. It's pretty much the opposite of the premises. Then you have the contrapositive, which is going to be if negating both and switching. So if not Q, then not P. All right, so here's a big star here. Do not assume the converse is true if the premise is true. We're talking about these two. All right, these are one-way streets. Okay, we can't assume that these are true. They may be in certain instances, but you can't just assume that. You falsely believe a one-way premise also goes the other way. In some statements, they do go both ways. Those are the if and only if statements, or if. We have this little symbol that we have here. It's just an open line with two arrows. One going to the right, one going to the left. It's open. So example of that. The book gave a good one here. Measure of 90 degrees if and only if the right angle. So a right angle is 90 degrees. A measure of 90 degrees is a right angle. Always. These are proven. So that's the summary of 7D.